Okay. So study this is called fluid dynamics. We've already said this, but fluid includes all things that can do what? They flow, right? That's the root of the word, is to flow. And flowing things include liquids and gases. So all liquids and gases are fluids, but we'll see that actually that we're only dealing with liquids, and not even all liquids, but just a subset of liquids. Because we're looking at an ideal fluid flow, we'll need to look at these different characteristics. I think I had a quiz question about this. Did I have a quiz question about characteristics of fluid flow? Yeah, I'm trying to put it out of your head, aren't you? Okay. Yeah. Number 4, about the volume doesn't change. Yeah. Did I get that one right? Yeah, good. A lot of hundreds? You don't have to tell me. But you can tell me if you want. I'll know pretty soon. All right, so characteristics of fluid flow. Along the way, I'll circle the ones that are for an ideal fluid, but you can probably guess as we go through them, or you probably already know it. They can be steady or unsteady. An ideal fluid flow, which is what we'll be dealing with, means that the velocity at a point doesn't change. And the important thing here is at a point, because we'll find that the velocity of our fluids will change quite a bit depending on their scenario. But what we're saying is that at one point, at that particular point, or any one point in the fluid, that the velocity will be constant. Rotational or irrotational, which one of those is a characteristics of an ideal? Irrotational, right? It doesn't rotate. Yeah, that's a funny prefix, isn't it? Ir. Are there other words that have that as a negative prefix? Irregardless of what? Irrational? Well, there are a lot. I just thought it was that one word. But I guess anytime you have a word with R, it takes the IR prefix. Is that right? It sounds right to me. I just made that up. I think it might be true. Irrotational fluids simply don't rotate. Can you think of a good example of a rotating fluid? You can, you're just too embarrassed to mention it, right? The toilet. When you flush the toilet, that's a rotating fluid. And so that's, were you thinking of something else? What was it? Okay. Anyway, so that's a rotating fluid. It's not ideal. We're not going to consider that. We'll just think of fluids that flow in a straight line. And then viscous or non-viscous, we're looking at non-viscous fluids. Viscosity describes the friction between the molecules. That was straight from the book. Right, the ones that I'm circling are ideal fluid. I think I'll talk about this in a bit. All right. Yeah. So some non-viscous fluids, for example, water is a fairly non-viscous fluid. Most watery things. Can you think of viscous fluids? Oil, grease, syrup. Blood is also somewhat viscous, and so later we'll talk about how that impacts the flow of blood. Although we'll consider blood flow to be an ideal flow, although it's not exactly an ideal flow. We'll find that actually there are unsteady flows, rotational flows, viscous flows of blood through the body, and turbulent flows. Compressible or incompressible, we're looking at incompressible is an ideal fluid. That just means that when you apply pressure, the volume is constant. So incompressible fluids are liquids. Compressible fluids are gases. And then laminar versus turbulent. The fluid flows in parallel layers. Or you can imagine it flowing in parallel layers with no interaction between the layers. The layers, well, have you ever seen a video of one of those air tunnels? They put the car in there and then they put the smoke to go around the car. I'll draw a picture. Where if you have a car and they send these layers of fluid around the car, they use smoke to sort of track out where the fluid goes. And so you get these non-interacting parallel layers of smoke or fluid that go around the car. The point is that they don't interact. That these two layers of fluid, as they flow, they'll never come together because they are a laminar flow instead of a turbulent flow. The layers near to the sides of the pipe will move more slowly. So if I have a pipe with different layers of laminar flow, the sections over here on the side will move slower. It's like those parts of the liquid or the fluid will stick to the sides of the container. And so it slows them down just a little bit, and here in the middle, it'll go faster. Usually this occurs for viscous fluids at low speeds. Because viscous fluids, the viscosity, remember, describes the friction between the molecules. And if it's just a stickier fluid, if it has more friction, then that means it's going to stick to the sides of the pipe more. And this usually occurs at slower speeds. At faster speeds, it just doesn't stick as much. And most blood flow is laminar. But we'll find that there is one part of our circulatory system that's not really laminar at all. Do y'all know where that is? In the heart. So we have very turbulent motion in the heart, where all those layers get all mixed up. But as it goes through the veins and the arteries, that it's fairly laminar. In turbulent motion, these layers will interact unpredictably. If you're a scientist and you study the flow of fluids, usually if you want to predict what turbulent motion is going to do, you have to use a computer program to actually run through each step. There's not really a law that just says, okay, this is going to describe all situations of turbulent flow. The velocity of the fluid changes a lot. And sometimes blood flow is turbulent, such as in the heart when it contracts. And when that happens, blood rushes quickly into another chamber. Of course, that makes a distinctive sound. I don't know what the sound is. What is the sound? Y'all know this. No, it's not the heartbeat. It's something, the swoosh or something. What's it called? Come on, y'all are allied health folks. It doesn't matter. But it makes a distinctive sound. You can hear it when you're listening. Okay, so which of these is not a characteristic of an ideal fluid flow? You can use your notes. The one on the left. Which is not characteristics of ideal fluid flow? Okay, y'all are sort of split. You can look back in your notes if you want. It's just on the very previous page, I think. Is it the previous page? Yeah. All right, let's stop at 50 seconds. Ask your neighbor if you like. Okay. No, wait a minute. Yeah, so all of these are characteristics. So this was laminar versus turbulent, irrotational versus rotational, steady versus non-steady. You don't have to write these down if you don't want. There's just our viscous versus non-viscous versus viscous. And all of these are properties of ideal fluid flow, and all the others are not properties of ideal fluid flow. All right, liquids are what and gases are what? Compressible or incompressible? By the way, I went to a seminar last week, and they were talking about how to create the perfect multiple choice question. And they said that you should never use all of these or none of these. And I was sort of surprised by that. I like using those, but I think most students think that that's never the answer. Is that right? Y'all think that all or none is not usually the answer? It's not true, right? It's not true. Is it usually the answer?
Yes.
No, it's not. I do it all the time. It's not my answer. Okay, not on my test. Huh? Oh, yeah, it doesn't count for me. All right. So let's stop at 55. 55. Oh man, you all got it right. Oh, one of you snuck in there, huh? That's okay. So C is the right answer. Liquids are incompressible and gases are compressible. So the police came by my house this morning and they knocked on my door. And I come to the door and it's like, sir, can I have a quick word with you? I said, sure. How about velocity? You'll get it? That's a quick word. Okay, so no. Generally, anytime we talk about a rate, anytime we're talking about a rate, we mean something, how something changes with time. Like you had a question, I think, didn't you, about volume flow rate? Oh yeah, so when you pump gasoline into your car, the flow rate is about 3 gallons per minute. And I asked you to describe the fluid, or what is the definition of flow rate. So in that, you sort of had to know what gallons was, or you had to know what a flow rate was. But it was a what per time for flow rate? Volume per time. Gallons is a measure of volume. It's not a measure of area, weight, or mass. It's a measure of volume. So a flow rate refers to how a flow of fluid changes with time. We're going to use Q to represent flow rate, and we're going to let Q be equal to volume per time. Okay, so remember that. Q is flow rate. And later we'll use that to describe, we'll look at some different equations that affect the flow rate. In a pipe, the flow rate must be the same in different parts of the pipe. So if I have a pipe and I have a flow rate over here of 1 cubic meter per second, that means that I have a cubic meter of water. Well, these squares on the floor are about a square meter. So you can imagine a cubic meter is like a box about this size that's filled with water. That would be a cubic meter of water. And every second, that cubic meter of water moves past the point. So this whole thing will move over here in 1 second. That would be 1 cubic meter per second. And so if I have a cubic meter per second moving past this point, a cubic meter moving past this point every second, then I also have to have the same here and here and here. Because as that cubic meter moves down the pipe, it's going to displace the fluid in front of it, right? So here's my cubic meter. It moves in 1 second, and in 1 second again, and in 1 second again. So I have to have the same flow rate throughout the entire pipe. So I have 1 cubic meter per second over here, and then on and on and on. That might seem obvious to you here because the pipe doesn't change shape. But it's also true that if I have a pipe that gets bigger, then I'm still going to get a cubic meter per second throughout. So if my flow rate is Q1 over here and it's Q2 over here, then Q1 has to equal to Q2. And that is the flow rate equation. But anytime I have a flow rate here, which is a measure of the volume per unit time, it might be cubic meters or gallons or, I don't know, liters per second, then I'm going to have the same flow rate over here. It has to be, right? Unless, of course, I have other pipes that are coming in, or I have a leak in the system where stuff is getting out, or if it's a compressible fluid. If it's a compressible fluid like a gas, then it doesn't have to be the same flow rate because that gas can get compressed along the way. Okay, so the flow rate equation then is a volume per time and it says that volume 1 over time has to equal to volume 2 over time. Well, let's look at this rate, this flow rate, which is volume over time. Remember early on, we described sort of a general way that we can think about volume. We said that volume can be expressed as an area times some distance. Like, for example, with a cylinder, the volume of that cylinder is the area times the height of the cylinder. So in general, when I talk about volume, I can think of it as some area, some cross-sectional area that's multiplied by some distance. Just thinking about it dimensionally. You remember that? Are you with me on that? Okay. If I look at the dimensions of those, area is in square meters, D is in meters, and so that's going to give me units of cubic meters, which is the same as what I have in volume. But just dimensionally, it works out okay. And so if I look at this, and I substitute here, instead of volume, I have area times some distance divided by time, I have something that stands out to me. What is this D over T? Remember what that distance over time represents? It's a quick word. No. You gotta hear my joke. What's a quick word? Yeah, it's the velocity or the speed. So the area times the speed is equal to the flow rate. Q then is equal to the area times the speed, or A times V. Okay, so in this pipe then, if Q1 is equal to Q2, A1 V1 has to equal to A2 V2. So, where is the speed greater? Let's do it as a quicker question. Is the speed greater in section 1, in section 2, or are they both the same? Or D, none of the above. Okay? Where is the speed greater? In section 1, that's right here, or section 2, right here. Now what I've done to the area is I've made the area bigger here, right? Area small here, area bigger here. So what happens to the speed? where do we have the greater speed? In section 1 or section 2? Or is it the same, or it's not D? It's either A, B, or C. In fact, it's not C. It's either A or B. What happens to the speed? Well, some of you had C, so let's address that. Because I did say earlier that the flow rate is always the same, right? The flow rate is always the same. Regardless of how big the pipe is or how narrow the pipe is, the flow rate will always be the same. But I'm not asking about the flow rate. I'm asking about the speed. The speed and the flow rate are two different things. Okay? The flow rate would be, I have this volume of fluid. How long does it take to move over to this point? That would be the flow rate. But the speed would be, how fast is it moving along? Those are two different things. Okay? So let's stop at 1:30. Yeah, most of you have it right, or many of you have it right. Where is it fastest, section 1 or section 2? Okay, more than half of you have it right. So A is the right answer. It is going to be moving faster in the smaller section. So this is my fast section. And slow. You can imagine why that is. If I have to have the same flow rate in both of these sections, if my volume per time has to be the same as it is over here, I just have to move faster to get the same volume through this small section of pipe. But in the bigger section of pipe, I can move much slower. There's just more space for the liquid to fill out. And so I'm always going to move faster in the smaller section of pipe than the bigger section of pipe. Have you ever used a water hose? Anybody? Did you? Yeah. You use a water hose? Yeah. And so if you don't have a sprayer on it, what do you do to make it spray? You put your finger over it. What are you doing when you put your finger over the end of that hose? No. Make what? No, not exactly. You're making the area smaller. All right, so if you make the area smaller, you just close off part of the hose. That makes it do what? If A goes down, if area gets smaller, then what happens to the speed? It gets faster. So if A goes up, if A goes down, if the area gets smaller, the velocity goes up. Let me write that in one more way. That AV is constant. That means that whatever I do to this side, I have to do to that side the exact opposite. If A is big, V is small. If A is small, V is big. That's called an inverse relationship. You don't need to know that word, but you do need to know how to operate with inverse relationships. If one variable goes up, the other variable goes down. Because this has to always remain a constant value. The flow rate is always constant. So if one of the variables goes up, the other variable has to go down. Big area, small velocity. Small area, big velocity. Expect questions about that on the test, and probably some calculations with it. That'll be with simple numbers. Okay. Let's try this. A little example. I have a pipe with a cross-sectional area of 20 square centimeters, and water flows through it with a speed of 30 centimeters per second. I'm going to write some of these down. A is 20 square centimeters. V is 30 centimeters per second. What is the flow rate, first of all? What is Q? Q is the flow rate. And if I want to know the flow rate, it's going to be A times V, or 20 times 30. And that's 600 cubic meters per second, or cubic centimeters per second. Y'all know what a cubic centimeter is? Another word for cubic centimeter? What does cubic centimeter start with? Cubic starts with a what? C. All right, cc. So a cc is just an abbreviation for cubic centimeter. Did y'all know that? Did you? You didn't know it? Is it obvious? It's not obvious to me. It could be something else. Maybe it is obvious, but a cubic centimeter is about this much volume. You know another measurement for a cubic centimeter? Milliliter. Who said that? Hackett? Yeah, so a milliliter is a cubic centimeter is a cc. Anyway, so this is 600 cubic centimeters per second. Then the pipe gets smaller. It goes to 10 square centimeters. What speed is it going to be traveling now? So my area initially is 20. I'll call this A1, this V1. A2 is going to be 10 square centimeters. Hey, if the area goes down, what happens to the speed? It's going to go up. It's an inverse relationship. So, and in this case, it's a linear inverse relationship. By whatever amount the area goes down, in this case by a factor of 2, the velocity is going to increase by that same factor. So what is my velocity going to be here? 60 is right. It's an inverse, I'll write that down. You don't need to know these words, but it's an inverse linear relationship. Inverse meaning that whatever happens to one, the opposite happens to the other. And linear meaning that it's the same factor. If it increases by 2, the other decreases by 2. If you really wanted to get into the equation, you would say A1V1 is equal to A2V2. A1 would be 20 times 30 equals 10 times V2. And then you would find that it would be 60, right? V2 is equal to 60. But don't worry about the equation. Just think about the relationship. If one goes up by a certain amount, then the other has to go down by that same factor. If one's doubled, the other's half. If one's tripled, the other's thirded it. If one is, half, the other's double. Y'all can do that, right? I know you can. Yes, you can. All right, so viscosity determines how thick a fluid is, and different materials have different viscosities. Temperature affects viscosity. Usually colder is more viscous. So I'll show you a video maybe today. Colder is more viscous. That sort of makes sense, right? If things get cold, they just flow less quickly, less readily. The viscosity affects the flow rate. Viscous fluids, like blood, which is kind of viscous, need a constant pressure to make them flow. Non-viscous fluids do not need a pressure. I don't know what words these are supposed to. I don't have them in my notes. I just have a line drawn through them. Superfluids have no viscosity and will move through. I'm sorry, I'm just making this up. I have no idea what I meant to do here. I'm not going to test you on it, but I want to show you a video, okay? Let's do these questions first, and then I'll show you the video. I guess last year I did the same thing because I didn't go back and look at my original notes to see what I meant to say there. I'm sorry. Take it out of my paycheck, okay? Let's try the one on the left. Flow rate has which of these units? Flow rate is change in volume over change in time. All right, let's stop at 43. 43. Come on, y'all. Just guess if you don't know. All right. All right, good. A is right. It's in cubic meters per second. That's a volume per unit time. And then water flows with speed V through a pipe. Its cross-sectional area is A. If the area of the pipe decreases to A over 2, what is the new speed of the water? All right, I'm going to stop at 43. Okay, C is right. If I decrease the area by a factor of 2, if this goes down, this has to go up. If this is divided by 2, this must be multiplied by 2. Because I know the product of A and B is constant. Whatever I do to one, I also have to do to the other so they cancel out. So I'm doubling the velocity, so it's going to be C is the right answer. Let me show you a video.